In the world of machine learning, sometimes the most powerful ideas are actually the simplest ones. Today, we're going to break down one of the most intuitive algorithms out there, k-nearest neighbors, or KNN for short. And what's so cool about it is that it's a way of making predictions that you probably already use in your daily life without even thinking about it. So, let's kick things off with a bit of a puzzle. Most machine learning models, right, they need this intense upfront training phase to learn from data. But what if an algorithm could just skip that whole step and still make really smart predictions? I mean, how would that even be possible? Well, the answer is surprisingly simple, and it's all built on an idea we just instinctively get. Similar things are usually close to each other. It's like saying birds of a feather flock together. KNN basically takes this very human idea and turns it into a powerful algorithm. Okay, so what is KNN at its heart? It all comes down to what I like to call the neighborhood principle.
Just imagine this. A new house gets built on a street that only has red houses and blue houses. If you had to guess its color, what would you do? You'd probably just look at its immediate neighbors, right? If most of the closest houses are blue, you'd bet your money on blue. And guess what? That is the exact logic that KNN uses. It's really that simple.
And this simple neighborhood logic is surprisingly versatile. It's most commonly used for what we call classification. Things like deciding if an email is spam or not spam. But it can also tackle regression, which is where it predicts an actual number, say estimating a house's price by just averaging the prices of its closest neighbor.
But hold on. How does the machine actually know what closest even means? It needs a way to measure it, and the most common way is something called Euclidean distance, which is really just a fancy term for the straight line distance between 2 points. Like how a crow flies. This simple measurement is how the algorithm figures out who is similar to who. All right, we've got the main idea down. Now let's actually see how KNN makes a prediction. We're going to walk through it step by step. The process is just incredibly straightforward. Let's follow along. Step 1, a new data point shows up, our new house. Step 2, the algorithm finds its k nearest neighbors. For this example, let's say k is 5. Step 3, those 5 neighbors get to vote based on their color. Here, we've got 3 blue votes and 2 red votes. So, what's the result? Step 4, the majority rules. The new house is classified as blue. It's just a simple democratic system.
Now, this whole approach is why KNN is famous for being a lazy learning algorithm. And it's not an insult. Unlike other models, it doesn't do any work up front. There's no training. It literally just stores the entire data set and chills out. All the heavy lifting, the distance calculations, the voting, it all happens at the very last second, right when you ask for a new prediction. It's the ultimate procrastinator of machine learning.
And one of KNN's biggest strengths, really, is its flexibility. Because it's just looking at local neighborhoods, it isn't forced to draw simple, straight lines to separate data. As you can see here, it can create these really complex, squiggly, adaptive boundaries that can perfectly hug the true shape of the data, no matter how weird or intricate it is.
So KNN is simple, but to get the best results, you do have to make a few smart choices. Let's talk about how you can tune this thing to work even better.
The single most important decision you're going to make is choosing the value of k. That's the number of neighbors the algorithm actually listens to. This one little number can dramatically change the outcome. And here's a pro tip for you. It's almost always a good idea to choose an odd number for k. Why? To avoid any ties in the voting process. Choosing k is a huge balancing act. On the left, if you pick a really small k, say k equals 1, you get this super jagged, complex boundary. It's really sensitive to every single little point, even the noisy, weird ones. We call this overfitting. It's like the model is memorizing the data instead of learning the general pattern. But on the right, if you pick a really large k, you get a much smoother, more generalized boundary. The danger there is if it's too large, it might blur out important local details, and that's called underfitting. The trick is finding that perfect sweet spot right in the middle. Okay, let's talk about a really common trap people fall into. Imagine you have features with totally different scales, like age, which goes from 1 to 100, and salary, which might go from 10,000 to 1,000,000. With KNN, this is a huge problem. Because of the way distance is calculated, a small change in salary is going to look way bigger than even a huge change in age. The algorithm ends up being biased and basically just listens to the feature with the bigger numbers. So what's the solution? Well, we have to create a level playing field. And we do this with a process called feature scaling. We use simple techniques like normalization or standardization to basically squish or stretch all the features so they're on a similar scale. This makes sure every feature gets an equal say in the distance calculation, so no single feature can dominate the conversation. So, we know how it works and we know how to tune it. The big question is, when should you actually use KNN? Let's take a look at the bigger picture.
If you look at this table, KNN has some really clear advantages. It's super easy to understand, there's no training time, and it's incredibly flexible. But the disadvantages are pretty significant. That whole lazy thing means it's really slow on large datasets because it has to compare every new point to the entire dataset. It also eats up a lot of memory. And this last one is crucial. It's very sensitive to irrelevant features. If you throw too much useless information at it, the whole concept of distance starts to become meaningless. It's a problem some people call the curse of dimensionality.
But hey, despite those limitations, KNN is out there in the wild doing some really cool stuff. Think about recommendation engines on shopping sites. Customers who bought this also bought. That's a perfect use case for KNN. It's also used in image recognition, finding anomalies in data, and even recognizing handwritten numbers.
So, what's the bottom line? When should you reach for KNN? It's an absolutely fantastic choice for smaller datasets, especially when you suspect the patterns are complex and nonlinear, and when being able to explain why a decision was made is important. But if you're dealing with a massive dataset or you need predictions in the blink of an eye, you're probably going to want to look for a different algorithm.
All right, let's just boil this all down. What are the key things to remember? KNN learns by looking at its neighbors. Distance is the core concept that defines similarity. That little letter K is the dial you turn to control the model's complexity. It's a lazy algorithm, meaning no training phase, and at the end of the day, it's simple, but it is a surprisingly powerful tool, especially for anyone just getting started with machine learning. And that brings us to one final big question to think about. We know KNN is simple and intuitive, but in our world of massive data where speed is everything, is lazy learning still smart learning? That trade-off between its beautiful simplicity and the demands of modern scale, well, that's something worth chewing on. Thanks so much for tuning in.